So now what is a classifier? What is a naive Bayes classifier? And why is it called naive? So let us start with the Bayes rule. We know that we have, let's assume we know x1, x2, x3, and x4. And this is our data. This is the input data, and then we are doing classification. For this example, keep in mind the iris data. So sepal length, sepal width, petal length, petal width. Given that you know the sepal length, sepal width, petal length, petal width, what is the class? Is it a setosa? What is the probability that it's a setosa? Okay, and you have three classes. Let's say you have k classes. Who cares? This could be three. So you can have three classes or more. This is hard to compute. If you know that, then you already know your classifier, and you're gonna be really happy. But the problem is that you don't know this, and it's not easy to compute this directly. So we're gonna compute this indirectly by using the Bayes rule. This is P of B given A is equal to P of A given B times P of B divided by P of A. And we are just switching the roles of X's and C's. So it's going to be x1, x2, x3, x4, condition on we know the class, probability of the class, and the probability of the class is easy to compute. Why? Because you look at your training data and count the number of times that setosa appears, and count the number of times that the second class appears, etc. And then you just divide it by the total number of observations, total number of labels. So this part is easy to compute. We just need to take care of this term, and this term doesn't depend on your class. I said you either compute this or you just ignore it when you are doing optimization. And because we are doing optimization, we don't need this term. It doesn't depend on C. So we can just get rid of that. So let's look at the numerator. The numerator is P of A given B times P of B. That's just P of A comma B. That's the joint distribution. This formula we saw up here. P of A comma B is P of A condition on B, P of B. And this is the other term. Okay, so we are just rewriting the numerator and using definition. So we are not making any mistakes there. This is pure math. It is perfect, no mistakes. Then you take that, you put it here on the left side, and then you rearrange your terms. It's gonna be P of x1 given x2, x3, x4, and ck. Now you're changing the definition of your A and B. This is now your A, this is your B, and this is your B. Okay, so we are just rearranging terms. No mistakes here. This is perfect, correct mathematics. Then you take this term and you do the same game with it. This is the joint distribution. You turn it into conditional distribution. P of x2 given x3, x4, ck, and the other term. Now you take this term, you do the same game to it. You take this, you copy it and paste it here, and then you turn the joint distribution into conditional distribution using definition. Now this term, you do the same thing. This is where the naive assumption comes in. Whatever that I did here is perfect mathematics, so there is nothing wrong with it. But then here is where the assumptions, the naive assumptions come in. The assumption is that if I know ck, then I don't need to know the rest of the features. It means that if I know the class is a setosa, then I don't need to measure the sepal length, petal length, and petal width to tell you what is the sepal width. If I know that the class is a setosa, then I don't need these observations anymore to tell you the size of x1. In some cases, this is a correct assumption. In some cases, it's a wrong assumption, but it's a useful assumption. So all models are wrong, some are useful. So a famous statistician said that long time ago. Okay, so this is where your modeling assumption comes in. You do the same thing. If I know ck, there is no need for me to tell you what is x2 and x3 for you to be able to know what is x2. Same thing here. If you know ck, there is no need to know x4. So these are the assumptions. You take that and put it into your formula up here. This is your formula. And then we are gonna, this is a constant. We are just gonna call that z, capital Z. We don't care about it. And this term, we are just expanding it using these formulas and these assumptions. So in the end, this is what you're gonna get. You're gonna get a constant, 1 over a constant, P of x1 given ck. This is this term, out of, after making the naive assumption, then P of x2 given ck, x3 given ck, x4 given ck, and p of ck. And this is just coming from here. P of ck, then p of x4 given ck, p of ck, p of x4 given ck. The next term is x3 given ck. We are dropping x4. The next term is x2 given ck. We are making the assumption that these two don't matter. And the last one is p of x1 given ck. That's this term here. And I mentioned that you want to maximize this probability to give you the correct class. Now your problem is, what is the class? Is it a setosa? Is it a versicolor? Or it's a third class? So you just maximize this with respect to k. And that's why I said, because this term zk, z doesn't depend on c, therefore you can just drop it. It's just a constant, shifting your objective function up, down, scaling it. Who cares? It doesn't matter. It's a probability, it's a positive term. You can just drop it. It's not gonna affect the maximum point. It's gonna affect the maximum value, but it's not gonna affect the maximum point. The arc here means the maximum point. So if you draw a function, your maximum is gonna happen at a point, and that's the arc. We are looking for the argument that's maximizing our function. And if you solve that problem, then it's game over. You know that the first class is giving you the maximum probability, and that's going to be your prediction. So far, your model doesn't have any parameters. What you do is you parameterize these terms. P of x given ck, P of x1 given ck, x2 given ck, x3 given ck, x4 given ck. You parameterize them with a normal distribution with a mean and a variance. So the mean and the variance are you're gonna have how many of them? 1, 2, 3, 4 mean and variances. And this last term, you just know it. It's just the number of setosas in your entire data set. Okay, is the math clear? Any questions? So what is cool about naive Bayes is that you don't have any hyperparameters to adjust. You have parameters, mu and sigma, that you have to train, but you don't have any hyperparameters. This is cool. In your linear regression, you had parameters. These are your parameters. You also had hyperparameters, like if you want to include higher order terms in your polynomial, where should I stop? What polynomial order? That's a hyperparameter. In our k nearest neighbor, k was a hyperparameter. This k that we consider of our neighbors is a hyperparameter, but k nearest neighbor doesn't have any parameters. So for k nearest neighbor, you have to carry your data with you all the time. For the regression model, you don't have to carry your data with you all the time because your data is now memorized in these parameters. It's summarized in your parameters. Similarly, for naive Bayes, you don't have any hyperparameters. It is perfect. It's awesome, but you have parameters. And the cool thing is that your data, you can throw them away and just memorize the mean and sigma of your data. So you can throw away your data. It's like a logistic regression model without any hyperparameters. So you don't have to do hyperparameter tuning. So each algorithm has its own pros and cons, has its advantages, disadvantages, and it's good to know all of them. Okay. Now let's look at our implementation. Where is naive Bayes implemented? In this library, E1071. You have to install and then load it. So installation in your computers might take a while, and you might have to, I don't know, debug your installation. But after you install it, you just load it. Then the way that you use it is very similar to the previous method. You just say that you want to predict species given the other data, given the other variables. And then you have to do training a little bit because you need to know what is your mean, what is your sigma. That's why you need a training data. You can take a look at your model. And these are exactly what I was talking about. This is your prior probabilities. 1/3 of your data is setosa, 1/3 of your data is versicolor, 1/3 of your data is virginica, and these are these P of CKs. And these are your conditional probabilities. And for conditional probabilities, what do we need? If I know the class, what is the probability of x4, for instance, sepal length? And then we are parameterizing it with a mean and a standard deviation. So the first one is a mean, the second one is the standard deviation. So this number we know, that number we know, and this is just the probability of sepal length, probability of x4, given that we know it's a setosa, probability that it's a versicolor conditioned on it being a virginica. And each one has its own mean and variance. So these are your parameters. Similarly for the other variables, this is, I don't know, x3, this is x2, this is x1. Now when it comes to prediction, that maximization problem is going to be solved. During prediction, this maximization is going to get solved. And then you do the confusion matrix. It's making the same mistakes as before, and it's 88.88% accurate. Let's apply it on a more complicated data, the diamonds data. Let's take a look at the model. Now we have 5 classes: fair, good, very good, premium, ideal. One cool thing about naive Bayes is that it's going to take into account the imbalances in your data. So this data, unlike the previous one, is imbalanced. You have more observations of ideal compared to good and fair. It's going to take that into account automatically. And then these are your variables: x4 given fair, good, very good, premium, ideal, given the class, table, x, y, z, log price, and log caret. You do your prediction. Now you see it's taking more time, okay, because it has to solve that maximization problem each time. Then you do the table, it's making some errors, some mistakes, and then that's your accuracy, 57. Okay, so far this was 57. The linear regression, logistic regression was 65 on the diamonds data, and the k nearest neighbor was 72. So it looks like the k nearest neighbor is more accurate on this data. Okay, we have 2 more minutes. In the meantime, are there any questions? Next session, we are going to start neural networks, and we're going to go over that. That's another advanced topic. I'm going to introduce it in this course, and then later on, you're going to learn more about it, more about different types, etc. That's going to be next session. I'm going to be around for those of you who have questions, and the ones who want to leave are more than welcome to leave.